Hello everyone, this is Rizvi. I'm going to present our work titled Anycast Agility, Adaptive Routing to Manage DDoS. This is a joint work from USCISI, University of Twente, and SIDN labs. DDoS attack is increasing and it is getting worse day by day. We can now see 2.3 terabit per second attack, and there are lots of cheap services that can make these attack events with a little cost. Malicious entities can make these attack events without requiring proper technical knowledge. Scrubbing systems are popular for DDoS defense using third-party services. However, these services can be expensive, and the operators sacrifice some kind of control over the traffic. In this work, we focus on Anycast network like SIDN DNS, where we want to utilize the capacities in other sites by spreading the traffic. This is something that other third parties do, but they haven't described it formally. Anycast divides the whole world into multiple catchments, and the same service is provided from multiple geographic locations. You can see from the figure that the clients are distributed among 3 Anycast sites distributed in 3 continents. Anycast is widely used by many CDNs like Akamai, Cloudflare, or Google, but the only way to control traffic in Anycast is BGP. Our goal is to utilize BGP when we are under attack to mitigate the attack event. When there is an attack event at an Anycast service, it is possible that the attack overwhelms only one or few sites and keeps other sites unaffected. As you can see from the figure, that the red site gets affected and becomes unhappy. When we have such an attack, let's think about how the operators should respond to this attack. First, we can just absorb the whole attack into one site and keep other sites unaffected. In that way, only one site will be unhappy, but the other sites are happy. However, when multiple sites are affected, absorption-based technique is not that much helpful. Second, when other sites have extra capacity, we can try to spread the load among other sites. In this way, we can make all the sites happy, which is shown in the left figure. Lastly, in a specific scenario when a specific site has excess capacity, we can shift the maximum load towards that Anycast site. You can see such a scenario in the right figure where we push the traffic towards the bigger green site. But how to absorb, spread, or shift? We will see this soon. To demonstrate how spreading works, we are showing an animation here. This animation is from our colleague Leandro. We have 3 Anycast sites in 3 continents. Now, normal traffic is shown in the right panel. Now, we can see an attack just get started. Right panel shows overloaded Amsterdam site. Now, automated defense is triggered. It unloads Amsterdam site. An operator can control traffic in this way. Okay, now how do we know what to change to get this kind of outcome? We will show this later. Before making any decision, like the operator made in the previous slide, we need to know how much is the total traffic that is coming to our service. This is useful to make any decision. However, it is hard to measure the true offered load because of the upstream losses. In this slide, we are showing one such scenario. Here, there are 3 Anycast sites represented by 3 buckets where each Anycast site has a capacity of 4. At first, the incoming traffic is 3 units, and from the observation point, we can see those 3 units. Then the attack starts. Attack intensity was 4, which makes 7 total units of offered load, but our capacity is 4. From the observation point, we will be able to see 4 units, which is equal to the capacity, but we are still missing 3 other units which will be dropped in the upstream. So the observation point gives us an underestimation of the attack. In this work, our contribution is to propose a way to estimate the true offered load. After that, when we know the true offered load, our desired outcome is to utilize the traffic engineering techniques in a controlled manner so that no bucket is overloaded. We show this in the right side where no bucket is overloaded. Can we achieve this desired outcome in real-world events? We will answer this question later in this presentation. We need different BGP announcements for controlled traffic engineering. The last challenge is to utilize BGP precisely since BGP is not predictable. BGP is uncertain because catchments are the result of a distributed computation of everyone's routing policies. No single ISP knows it all. If we select a random routing approach or select something based on our assumption, then we might observe unwanted consequences and might overwhelm other sites. So in this work, we suggest to keep a BGP playbook to know all the routing options and their consequences. In this work, our first contribution is to estimate the true offered load when we have loss in the upstream providers. Our second contribution is to define and design a BGP playbook which will help us to take decision during a DDoS attack. Finally, we show that a BGP playbook can help us to mitigate real-world DDoS events. So our first challenge was to estimate the true offered load. We utilize known good traffic like RIPE, built-in measurements during normal and attack time to infer the total offered load. Here we are showing an example about how we measured the true offered load. At first, we assume the capacity between the router and the server is 100 megabits per second, and 50 megabits per second is the normal legitimate traffic. Then we are getting an attack with 150 megabits per second, so the total offered load is 200 megabits per second. Second, the capacity, since the capacity is 100 megabits per second, we will see a 50% drop in both legitimate and attack traffic. Because of this loss, we will now observe only 25 megabits per second legitimate traffic when we normally observe 50 megabits per second legitimate traffic. So we are observing around 50% of the total load. As the server runs in capacity with 100 megabits per second during the overloaded condition, we can estimate the true offered load doubles of it, which is 200 megabits per second. For manipulating BGP, we used 3 traffic engineering techniques to change the catchment distribution. We use path prepending, community strings, and path poisoning. These techniques have different trade-offs in terms of availability and control. We show more details about these trade-offs in our paper. We built a BGP playbook by combining all the possible traffic engineering techniques. We built this playbook prior to an attack event, and we use this table to select the right routing approach. We discovered traffic load using the existing tool Vertholdo that actively probes the network. Here you can see a sample BGP playbook. The playbook was built with a 3 sites Anycast service. Each entry in this table indicates a specific BGP routing option and the corresponding traffic distribution. Since catchment distribution remains stable most of the time, we can use this playbook for a week or even for a month. We validate and show different experimental results to prove our contribution. Due to time constraints, we show the key results here. We showed how losses cause underestimation and the methodology to estimate the true offered load. But does our estimation work? To answer this question, we evaluate an attack from November 2015. We estimate and compare the estimation with the reported rates. November 2015 event was a huge attack event where we observed around 94% loss in Beirut. After the loss, we could only observe 0.35 megaqueries per second traffic from the Beirut captured traces. Using the comparison, we then estimate around 5 to 6 megaqueries per second, which is close to the reported rates from other root servers. So yes, for this event, we could successfully estimate. We show more such cases in our paper. Next, we show how we used a playbook to defend a real-world attack event from 2017. This event was, had around 120 kiloqueries per second rate, started from 0 second, as you can see from the figure. We assume each site can handle around 60 kiloqueries per second rate. We use artificial capacities here in this experiment, but it is what would happen if the attack magnitude increases. The hatched area shows the overwhelmed Amsterdam site. Next, we will look into the playbook to find routing approach. So the problem is we are getting around 120 kiloqueries per second attack when our capacity is around 60 kiloqueries per second. Our goal is to keep around 50% of the load at each site. Now let's consult with our playbook. We can see several routing approaches that should work, marked by the ticks within the green circles. Several routing approaches will not work as well, marked by the cross signs. We select to announce only to transit 1 so that the traffic gets redistributed. Next, we show the impact of this selection. So we use community strings to announce only to transit 1. We expect to get less traffic at Amsterdam site since we are using only one transit provider. The figure shows the outcome after the propagation of the announcement. As you can see, there is no hatched area after 300 seconds, and no site is now overloaded. So using community strings from the playbook, we could mitigate the attack event. Our approach works for several other attack events as well, and we describe those events in our paper. In conclusion, we suggest that the Anycast operators to keep a BGP playbook, and we show the requirements of estimation and the possible impacts of a playbook to mitigate a DDoS event. Our artifacts are publicly available online in the provided link. Thank you all, and I'm ready to take questions.